Hello, pre-calculus students. This is Mr. McAllen, and right now I'm going to do a video of the review that we had in class today. Hopefully this will help you with any questions you may have for solving log and exponential equations. So I'm hoping this is of help. First of all, in class we worked on plotting these functions with transformations. So I want to just remind you what I'm looking for on this. I'm looking for the asymptote. I'm looking for the point that would normally be at for 3 to the x to be, normally it's at 0, 1. I'm looking to see where that point goes and where the asymptote goes. So it's clear from this that the asymptote moves to -2, and the point, the whole transformation for this function, we went left 2, down 2. So the point that normally is at 0, 1 should move to -2, -1 by looking at the transformation. So at -2, -1, that would be the point, and then I would draw the exponential growth function this way. Now, some people pointed out to me that when they were using additional points, when they were plugging, the point x equals 0 into this function, they were getting the coordinate 0, 7, and that's absolutely correct. So what I handed out in class, the function is quite a growth function because it's a base 3 function, and that's what it would be that's what it looked like. It'd have the point 0, 7, and it would have the other point -2, -1, and make sure you label your asymptotes. On the next problem, where we have the log function, we have a y-axis flip, and we have a transformation where the asymptote moves to 3. So we would draw our asymptote at x equals -3. We would have a point at 2, 0, and there's our log function, which has been flipped about the y-axis. So remember to answer all these questions about domain and range and boundedness and end behavior. Remember, end behavior has to be done with limit statements. So this function here would have the limit as x goes to -infinity. The function would equal infinity, and there would be no limit on the right-hand side because the function doesn't go beyond that asymptote. So moving along, this one should be easy. This is the initial value. It's growth because it's growth at 2% because we have a times 1 plus the rate to the x equals the the function value. So over here we want to solve this equation, and for this equation, 2 to the 10 minus 2x equals 16, you should have 2 to the 10 minus 2x equals 2 to the 4th. When you can switch to the same base, you can just set the exponents equal. So we would then proceed to say, 10 minus 2x equals 4, and 2x would equal 6, x would equal 3 in this case. And you should try that out just to make sure. So when you plug 3 in, you end up getting 2 to the 4th equals 16, which is correct. Moving along, we have a natural log problem, and we have natural logs on one side and on the other. What's important to do is you need to compress the logarithms so that you have one logarithm equaling one logarithm, or one logarithm equaling a number, and then you can use inverse function properties to solve the rest of the problem. So in this case, I have natural log of 3x equals 1 natural log of 4 times x minus 3. We're going to just write natural log of 3x equals natural log of 4x minus 12. And if we use the base e function, that's going to get rid of the natural logs, and we're going to be left with just a linear equation of 3x is equal to 4x minus 12. X will equal 12. Moving along to these problems, I don't know if you had a chance to try them all during class, but this first one, 2 ln of x equals 12, equals 7, subtract the 5. ln of x equals 7 halves. So then x equals e to the 7/2. I just use I use e to be the exponent. I'm sorry, the base for both sides to undo natural log, and I get 7/2 e to the 7/2 power. The next one I could raise both sides to x, so I have 2 equals x to the 1/2. Okay, so remember I used the inverse function of log base x. That was base x exponential. And now x has got to be 4 if I square both sides. The next one, since I don't have a calculator, I'm trying to make the base the same. 3 to the 3x minus 1 equals 3 to the 4th. And now in this case, it's just that 3x minus 1 is equal to 4.
Any available custodian, please report to the main office. Thank you.
On the next one, this is one that if I gave it to you like this, I would expect you to solve it, but things would have to be in terms of logarithms. So you use log base 2 of 2 to the x minus 4 equals log base 2 of 6. So now that you did that, you get rid of the base 2 logarithm on one side. We have x minus 4 equals log base 2 of 6, and then your answer is going to be log base 2 of 6 plus 4. This is clearly one that can be done without a calculator, but if I had given you some sort of an exponent expression like x plus 6 up in the top, you would not be able to do this without a calculator. You would need to use a calculator and logarithms to finish that problem, as this example shows here. So on this one, I wouldn't necessarily give you that problem. I would what you would end up having to do, I would change this problem so that this was maybe this was 8, and then if it was 8, you would have 4 to the 5x equals 2, well, I'm going to write 8 to the 2x minus 1, and then you would write this is 2 squared to the 5x equals 2 cubed to the 2x minus 1. And then you would, because you have the same base exponent, you could say that you have 10x, remember multiply these powers equals 6x minus 3. Don't forget to distribute that 3. And you would solve, you had 4x equals negative 3. X would equal negative 3/4. This one over here is totally solvable without a calculator. It just turns real ugly. So you got log of x times x minus 5. You compress the logarithms equals 6. Now you say x times x minus 5 equals 10 to the 6 because you're raising both sides to the base 10 exponential. So now this is x squared minus 5x equals 1 million. And that's, I don't know, I have never had to factor something so enormous. So I don't know what the answer to this riddle is as far as what multiplies to 1 million but adds to negative 5. I would probably go with the quadratic equation at this point. So, but that's how you would get it down to that step. I can't write here. So hopefully that helps. This one again, 2 different bases. I can't really do that to you because you won't have a calculator to help you do the log of or natural log on that. So that's something that would be probably safe for a calculator type question. On this one, however, you know, if we compress the logarithms, number 7, and I have natural log of 4 times x minus 6, we can just again use e for both. And oh, this looks familiar. I hope I didn't do this one already. Yeah, I think I did. Is that the same one? It's the same one. No, it's not the same one. It's really close though. All right, well, so let's just finish it up. It's really close. It's the same exact problem except for a 6 and a 3. So I have 4x minus 24. So I have x equals 24. So, you know, sometimes I lack creativity with some of these problems I'm doing. Now we're on to the open-ended. These are the ones that I did not provide you solutions for. So let's just go through this. Initial number of students, plug 0 in, because that's what the initial time would be for an initial amount. If you plug 0 in, you get 200 over 50. The initial number would be 4 people knew the rumor. How many students in the room after 2 days? You plug 2 in. So you would have your calculator for this. You just put 1 plus 49 e to the negative 8. Hopefully that value has meaning. I'm just wondering what that value would actually be. I would take out my calculator and calculate that. The next one is, when will 100 students know the rumor? That's just solving the equation. You have 100 equals 200, 1 plus 49 e to the 4t, and you're solving for that time value. How many students are in school or at the school? Well, that is a disguised question for carrying capacity. There are 200 people in the school because that would be the maximum quantity of students that could know the rumor. And the last question, well, actually there are 2 more. So the last question, we did this in class where we solved for the constant, but I'm just going to show you how to do this again. For part A, we have an exponential growth function where we have 0, 3, and we have 15, 5. And what we do for this problem is we have our basic exponential model where P of t is equal to a b to the t. So your initial value is the a value, so it's really 3 b to the t, and that equals your population. So now you put this data in, so that would mean that you have 5 equals 3b to the 15th. This requires you taking the 15th root to find b. The 15th root of 5/3. How you do that? You do 5 over 3 on your calculator, parentheses, you raise 2, and you make sure you enclose 5 over 3 as the power you're raising that to. Oh, no, 15, 1/5. Okay? No, 1/15th. There we go. That's the right answer. Sorry about that. So that would help you get the value for the b constant. Now, if you were going to do this with exponential, let me just erase or minimize this. Let's see if that'll work. Yeah, we can shrink all that. Just put that over there. And if you were going to do that with the exponential, you'd have P of t equals your initial amount e to the kt. So what we do in this case is we're going to, we know the initial amount is 3. E is the base exponent we want to force to use. So we can force e to work with this as long as we find the right value of k. So k t. So now in this case we're going to solve for k. So we're going to use this point 15, 5 again. So you have 15 equals 3 e to the k times 5. Now this is where I think I did something wrong here. 15, it was 5, not 15. That's 5, that's 15. So 5/3 shows up again as being equal to e to the k times 15. We natural log both sides to get rid of the e function. And that equals ln of 5/3 will equal k times 15. And now our k value is 1/15th of the natural log of 5/3, which is totally computable with a calculator, but that's basically how you run part B to find what the value of those constants would be. And they say here to use 3 decimal places, so do that with your calculator. I'm sure you can all do that. And the last part, let me just erase or minimize this. So the last part is the problem asks, the concentration of a drug in a patient's bloodstream T hours after injection is given by this function. So it's exponential decay because of the negative. What is A? Well, you should know by now that A is the initial concentration. So, but we have to solve for it because we don't know what it is. So they give us some information. They say C is equal to 2 when T is equal to 1 at 1 hour, right? So, so we solve for it. We say, okay, 2 is equal to A e to the negative 0.5 times 1 hour. So I have e to the negative 0.5, A equals 2. A will equal 2 over e to the negative 0.5. If I were to grab my calculator, it's going to take a minute to start. So we'll just wait. Wish I had Jeopardy music playing in the background. Oh, here we go. Calculator's up. So the problem said 2 over, so 2 divided by e to the negative 0.5. Let's see what we get. And it says our concentration was 3.29. So the 3.297. So I'm going to write down A was equal to 3.297. What is the initial concentration T0? Okay, so what is the initial concentration? That is what the A value is. That's kind of like a redundant question, just trying to make sure you understand what the A value actually represents. What's the concentration after 2 hours? Well, then you would take the function C of t. Now you have all the variables defined. 3.297 e to the negative 0.5 t. You would plug 2 in there for that. And this would actually be e to the first power, negative first power. So this would be like 3.297 times e to the negative 1. So we'll go back to the calculator. 3.297 e to the negative 1, and that's going to give us 1.213. So concentration at 2 equals 1.213. So what's the average rate of change over the first 2 hours? Well, average rate of change is a slope. So this is like kind of like applying some of our principles of, you know, average rate of change. So you want the concentration at 2 minus the concentration at 0 over 2 minus 0. So the average rate of change would be at 2 is 1.213 minus the initial amount, which was 3.297, all over 2 hours. So that would be the average rate of change of the concentration. So that would be, well, let me just go back to my calculator. That would be this quantity. Oh wait, let me clear that. That would be this quantity minus, let me go up to the first one. So look, I don't have to worry about that one. So I'm going to hit enter. So that's my change in concentration divided by 2 hours. And so my average rate of change is going to be, oh, lost it, negative 1.0422. Oh, sorry, Desmos. Don't need Desmos. 1.0422. What are the units on this? Milligrams per milliliter per hours. Milligrams per milliliter per hours. That's the average rate of change. Okay, this video has been much too long as far as what I was hoping for. I was hoping for 15 minutes, but I'm way over. So hopefully this helps you understand like the little ins and outs of solving these exponential equations. And you know, I look forward to hearing your comments tomorrow in class. And you know, good luck. Make sure you look this stuff over. Take care.